And without further ado, I would like to introduce this afternoon's session, Deep Learning on Disassembly Data. Please welcome Andrew Davis and Matt Wolf.
Okay, sure. Thank you. So I'm Matt Wolf. This is Andrew Davis. We are part of the data science team at a company called Cylance. If you're not familiar with the company at all, basically the best description of our Cylance, just to give you an idea, is it's the AI of AV. So our work focuses on applying machine learning for the purpose of malware classification. The research we're going to discuss here, just a disclaimer, is that the research we're going to show is different from what we have in our commercial product. So for people who are familiar with Cylance, I don't want you confused with this being our commercial product that we have. So just to make that clear beforehand. A little bit of FUD because it's Black Hat, so I want to scare everybody first. There's a lot of malware out there. So just from the Verizon report this year, 5 malware events occur every second. 79% of these samples are unique to organizations, and signatures are dead. So what this essentially means is that over the last decade or so, the volume of malware that's out there now continues to grow. And that causes a problem because you just can't scale in the traditional ways that we had before. So in the old days, in the very old days, an AV company would write a signature and then fax it to people, 20, 30 years ago. And so technology has changed over time, and now we have signature updates, and some other techniques are being used. But the main problem is if you're going to have a human in the loop to evaluate malware for you, evaluate a file, and let you know if it's malware, you just can't scale that up. So our goal, and part of this research, we'll talk about that, is we want to find automated ways that can detect malware and do it quickly and accurately. For this talk, just to give you a little bit of the roadmap, as I mentioned earlier, our focus is on artificial intelligence and machine learning. So we're going to give a brief overview of what that actually entails. I know some of you work in areas of AI here in this room right now, so for you, just sit tight. We'll get some good stuff later. But for the rest of you, we'll give you an overview of what it is so you understand sort of the context of what's going on. Then we'll talk about an area this research is focused on, which is deep learning, which is a subset of machine learning that has sort of grown in recent years to, has shown state-of-the-art effectiveness in various applications outside of security. And then we'll show how we apply that into the security space here. And then after that, the fun part is we're going to do a demo. So we're going to go to the internet, download a bunch of brand new malware that's been uploaded today to VirusTotal, and see how the model does. So you get an idea of the actual effectiveness that these techniques would have in the real world, right? And so with that, I'll introduce my colleague, Andrew Davis, and he'll walk you through the research he's done.
Check. Everybody hear me? Great. So could I get a showing of hands for the people who have been to the other machine learning talks here so far, just to sort of get an idea of how much I should get into? Okay, cool. So there's a good mix of the crowd who hasn't seen some of this stuff yet. All right, so the basic idea we're trying to address is, in advance, telling if something is good or bad. In other words, we download a PDF, we get something, an email attachment or something like that, and before we click on it, we want to know if this thing contains some sort of malicious code, right? So it turns out that telling good things from bad things is a very classic application of pattern recognition or machine learning. A lot of other people, like Google, uses machine learning to give you better search results. Facebook is going to use really cool, sophisticated algorithms to automatically tag faces and images. So there's a lot of good use of machine learning in industry. So if we have these very large databases of malware, right, and we know what we're looking at, we know if it's good, if it's bad, why don't we put these things to work? So for supervised learning, we need 4 main ingredients, right? We need input data, which in this case is going to be a whole bunch of, let's say, binaries, things like that. We need something called feature engineering, which is a way to sort of take this raw information, these raw executables or whatever input data modality is, and sort of crunch it into something that the model can understand. Then, of course, we need a predictive model. The model's job is to look at a whole bunch of data and then learn how it can tell between good and bad. And then we also need associated labels. So for every single input sample, we need a way to tell the model that, hey, this thing is bad, so you should try and call it bad, or hey, this thing is good, so you should try and call it good. So our input data modality can be a lot of things, right? In this talk, we're going to cover mostly executable code, so we're going to use Windows PEs in particular, but it's not necessarily confined to that. You could also use macros, so, for OS X, you could use Linux ELFs. There are all sorts of different executable types you could train a model on. You could also use these modeling techniques for documents, right? So you could see if a Word document is trying to do something weird. You could see if there's some malicious code in a PDF, or you could also see if Excel macro is trying to do something nasty. In addition, you could also use scripts, right? So if you have big scripts, you have a big script data set of, let's say, Python malware, you could train a model that could hopefully do well in Python. You could train a model on Bash scripts, Z shell scripts, Ruby scripts, whatever you want. Basically, as long as you have enough input data, you can probably train a pretty good model on it. So labels. The label is going to tell the model what the sample is. And in our case, it's going to be a very granular, just good versus bad decision, right? But if you wanted to do some advanced analytics, you could also have labels. Like, let's say you wanted to train a model to detect if something's banker malware or not. Or train a model that, it says, okay, this thing's probably a keylogger. You could train a model to do some more advanced analytics that way. So feature engineering. Feature engineering is vitally important to machine learning. In other words, the model that you have is only going to be as good as your input features. So as a motivating example, let's say we have a case where we're trying to break some new form of CAPTCHA, right? So this CAPTCHA is going to be 10 images. You may have seen something like this before. Each one is a cat or a dog. And presumably, if you're not a bot, you have no idea what a cat or a dog is, and you're just going to choose randomly. And the CAPTCHA isn't going to let you submit your form or whatever you're trying to do. So let's say we're trying to break this thing, right? So what we would do is, instead of dealing with the input image, which may be very complicated, cats have a wide variety of looks, dogs have a wide variety of looks. What you would do instead is you would write something to sort of break the problem into smaller chunks, right? So you'd have a thing that tells you, okay, is this object that I'm looking at furry? If so, it's sort of a true or false thing. Or does this object have floppy ears, for example? Or what is this object's approximate mass? So as you can see, none of these features are by themselves necessarily discriminative. So if something's furry, it could either be a sphinx cat or that weird looking dog on the side there. Floppy ears, that's not necessarily completely predictive as to whether or not it's a cat or a dog, and same with mass. So what the model would do is it would take these different pieces of evidence and it would find ways to sort of reason about it automatically so that it could tell you if the thing is a dog or a cat, and then you could break the CAPTCHA algorithm. So let's bring things home a bit and talk about the kinds of features that we would use for executables. So there are a number of machine learning-based approaches for detecting malware out there. So maybe what they would do is they would look at file size, for example. Malware tries to fly under the radar, so in a lot of situations it's very small. That's not necessarily true in every single case. You may have a very small file that's not doing anything malicious. So again, these features aren't necessarily by themselves completely predictive. You could also use strings. So you could run the Unix command strings against your file, then extract out all the strings that you see. And if the file is doing something like including a bunch of base64 encoded strings, or it includes a whole bunch of gibberish looking host names or things like that, the sample may be trying to do something nasty to you. We also have this idea called n-grams. An n-gram is a way to turn a variable length thing into a fixed length thing, right? So if we take the example cat is a variable length word, right? In this case, we have a word that's 3 letters long. And in the case of a 1 gram, we're going to turn it into a 26-dimensional vector. In other words, we have something with 26 bins. And for that particular word, we turn on the C bin, the A bin, and the T bin. And everything else is 0. You can also have 2 grams. So instead of a vector, you would have a matrix of things. And you would light up the CA bin as well as the AT bin. So unfortunately, n-grams tend to scale exponentially. So if you have a 2 gram, you need 26 squared storage. If you have a 3 gram, you need 26 cubed. And it just gets worse and worse. So n-grams kind of become prohibitive as you start increasing n up to numbers like 9 or 10. You could also use entropy of sections. So you would look at all your sections. If a section has very high entropy, that means it probably doesn't contain much executable code. It's probably packed or something like that. And again, being packed isn't necessarily indicative of whether or not it's doing something bad, but with the other evidence, like what the file size is and what kind of strings it contains, your model could learn how to discriminate between good and bad samples. So what is the model doing then? The model is going to take something in your feature space, in other words, the thing that you've engineered the binary to go into, and it's going to try and draw a line between the good samples and the bad samples. So the whole goal of feature engineering is to come up with a way that you can make all your bad stuff go to this side in your feature space and make all the good stuff go to this side in your feature space. And what the model is going to do is it's going to try and learn this dividing line between your good stuff and bad stuff. So there are a lot of models out there. The most simple one I can think of is naive Bayes. You may have seen naive Bayes in application to email spam detection. What naive Bayes does is it assumes that every single one of your features are completely independent, and it's a very small, easy to train model. You could maybe put a naive Bayes classifier on a really low-powered network switch to filter out spam emails, stuff like that. Then you have models that get more complex, right? You can have your more workhorse models like random forest, k-nearest neighbors, logistic regression, support vector machines. These are sort of off-the-shelf models that work well in a lot of general cases. And they kind of perform a good baseline of performance, right? So you take your data, run it through one of these workhorse models, and you can sort of get an idea of how well your model can do. Then we have more complex models, which is going to be the subject of this talk. They're called neural networks. Neural networks are nice because you can sort of tune the complexity of the model, right? You can make it learn really, really cool things, and I'll show you some neat demos of deep neural networks doing interesting things. So as I was saying, the whole point of the model is to learn sort of a separating region between the good stuff and the bad stuff, or whatever you're trying to classify. So to do this, you have to train the model. So the line may start off, see if I can get the laser pointer. I suppose it's not showing up on there pretty well. Okay, so I'll mime it. So the decision boundary may start off being something like this, and then over time, as it starts to look at more samples, the decision boundary will sort of figure out how to best move that line around so that it can divide between good and bad. So the whole purpose of this is to generalize to new samples, right? If the model can only tell us things that it knows about samples it's seen already, that's not very useful. We already have that, that's signatures, right? So the whole point is to generalize to unseen samples. So when you feed in a completely new novel piece of malware, if you have a good enough model, it's going to be able to tell you straight away whether it's good or bad. So I cooked up some animations for you. What we're seeing here is a model called logistic regression. Logistic regression is going to have the assumption that in whatever feature space you're operating in, your data is linearly separable. And if it's not linearly separable, then this line that it draws isn't going to perfectly discriminate things. But in a lot of cases, you can get some reasonable accuracy out of it. So as I was saying before, the initial condition sort of draws the line horizontally instead of vertically. And this particular model is being trained with something called stochastic gradient descent, or in this case, it's just gradient descent because I'm using all the samples. And every single time the line moves a little bit, it's because the model has said, okay, here are all my errors, and here's how I should move the line so that I better classify things on the next iteration. And it does this again and again and again until it settles into a local optimum. In other words, the performance where the model is going to be the best in the weight space or in the parameter space. And when it finally gets there, it's discriminating these red and blue classes with about an accuracy of 99%. However, there are some failure modes, right? Like I was saying, feature engineering is vitally important. And for a model like logistic regression, if your features aren't linearly separable, in other words, they're non-linearly separable in this example, it's not going to do as well, right? So as you can see from this toy problem, there's no dividing line that you can come up with that'll perfectly separate those two classes. You could have maybe something curved, but logistic regression isn't going to give you a curve. So you can see it has sort of a middling accuracy of like 88.6%. So what we're going to do is we're going to give it a more complicated model. And as this animation goes on, I'll sort of explain what's going on. So the neural network has the ability to sort of twist around and contort the original feature space so that it is linearly separable in higher parts of the model. That's not to say that no other models can do this. Things like support vector machines and random forest definitely do come up with nonlinear decision boundaries. But this is still a really cool visualization because you can see exactly how it's sort of sliding the space around in a way that it packs all the red stuff over here and all the blue stuff, sort of goes to the corners of the feature space. It's pretty cool to see. So When the model gets to the point of logistic regression, in other words, it says, okay, I've found something that sort of, mostly separates red and blue. It's going to say, okay, if I start bending the decision boundary down, then I can perform better. And you can see this one's getting 100% accuracy. Hooray, it's doing the job perfectly. So unfortunately, feature engineering, as important it is very, very hard. Excuse me. You need people who, excuse me. You need people who really know what they're doing. So you need people with a very long history in reverse engineering. You need people who know the file formats inside and out. You need to know all sorts of things to do feature engineering well. There's also this really fragile interplay between implementing the features in a way that's bug-free. So it's a very fragile process. So maybe we should ask ourselves if there are ways around feature engineering. In other words, some magical algorithm that we just dump data into and it gives us good output predictions. So are there ways around feature engineering? Yeah, I would say so. If you have a whole lot of data and you have a whole lot of computing power and you take advantage of these advances in deep learning or representation learning algorithms, you can usually do quite well. So with that, I'm going to get into deep learning. Like I said, I'm not going to ambush you with the math straight away. I'm going to give you a whole bunch of really cool motivating examples to maybe convince you that deep learning is a complex model that will apply well in the field of malware detection. So this is sort of the turnaround point for neural networks. This was a thing that happened in 2010. It was the first case of neural networks sort of working much, much, much better than the sort of existing solutions in computer vision. So hopefully you can see the labels well enough here. It's correctly classifying things like mites and container ships and motor scooters and leopards. In fact, with this challenge, there are 1,000 output classes. So the things that it needs to be able to, say what it is very wide and varied. So what's really cool about this is that when it outputs something like mite, it also has a couple of additional outputs. So these models are evaluated on how well they guess this top 5 accuracy. So as long as the correct label is in the top 5 output predictions, it counts it as correct. So when it outputs something like mite, you can see that the other labels are very related, right? We have black widow, we have cockroach, we have tick. With the exception of starfish, everything is pretty closely related. So in a sense, this model may be learning something about the world, right? It's saying that mites are very similar to these other buggy things. Container ships are very similar to lifeboats and amphibians. Motor scooters are kind of like go-karts and mopeds. And it's doing this completely on its own. All it has are input pixels, and then the output labels is what it's learning from. So the next evolution of this was automatic captioning. This work has only been going on for about a year or so. And the idea with automatic captioning is there's this huge data set of input images, and then the labels for these images aren't the object you're looking at. The labels are a human-made, I guess, annotation of the image. And the idea of the model is you're training it to look at an input image and replicate the caption that a human gave it. So you can see examples like man in black is playing a guitar, or a construction worker in orange safety vest is working on a road. The really cool thing to point out about this is that this model has never seen these images before. It's the very first time it's seen a construction worker in an orange safety vest working on a road, and it's outputting the correct thing. There are some kind of weird ones, like a boy is doing a backflip on a wakeboard. Yeah, he's doing a backflip, but it's not on a wakeboard. Of course, there are some failure modes of these models. So a cat is sitting on a couch with a remote control that kind of looks like a rat to me. Maybe close enough. A woman holding a teddy bear in front of a mirror. I don't see any teddy bears. I don't see any mirrors. So I have no idea why it's coming up with this. Then my favorite one is a horse is standing in the middle of a road. There's no horse whatsoever. This model's just getting it dead wrong. So clearly there's some room to grow with these models. Another really cool thing is a recurrent neural network. It's a special deep network that has recurrent connections so it can model time series data. And it's applied to the objective of language modeling. So with language modeling, you're going to look at the last, let's say, 10 or so characters. You're going to see some history of characters. And the objective of the model is to output the next character that it's likely to be. So you dump a whole bunch of Shakespeare into this model, and it completely memorizes things like character names, Pandarus, Second Senator, Duke Vincentio. And it's also coming up with things that are very structurally Shakespearean, right? So words like strain, words like attainted. So it's really interesting to see it sort of mimicking Shakespeare. Of course, like on a local level, it's is, looking a lot like Shakespeare, but on a global level, it's not really coming up with an overall story of the play. It's just outputting Shakespearean gibberish. Another kind of funny one is Paul Graham blog posts. You can see it's talking a lot about angel investors, startups, things like that. These models are actually stochastic. There's a bit of randomness to them, so you can sort of make them output more predictable things by changing how it samples. Anyways, so the funny thing about the Paul Graham blog post is if you make the model super deterministic, it gets stuck in this loop of talking about startups. I think it says something like about the startup, about the startup, about the startup. It just turns into a broken record. And the final one is deep neural networks trained on Linux kernel source. So in this case, you can see that it's doing a very good job of balancing curly braces, balancing parentheses. It's, it knows what pointer dereferencing is. It knows about structs. There's kind of a funny thing where it's returning 0 in a static void. But, we can cut the model a little bit of slack. It's, again, this is gibberish. If you tried to compile this, nothing would happen most likely. But it's really cool to see that it can output C. Like, if you were just to hand me these functions, I would totally be fooled and think it's some low-level C code. So now that I've shown you that, I'm going to introduce what's going on sort of mathematically in a deep neural network when you go from an input vector to an output label. So what I have on the left side here is a set of input features. So the top node is going to be file size. Next node is going to be section 1 entropy, let's say section 2 entropy, section 3 entropy. Then we have a whole bunch of other features, which I haven't listed. Then we have a final feature like, is packed with UPX or something like that. What we're going to do is we're going to encode that as a vector, and we're going to do a matrix vector multiplication on it, right? So that turns a vector into another vector, and then we're going to apply a nonlinearity, in other words, just some function, to every single one of those outputs. And then we're going to do that again with the previous hidden layer into another weight matrix. We're going to apply this process again and again until we finally get to the output layer. So you can sort of think of it as just a whole bunch of repetitive operations of matrix multiplication and nonlinearities. And this actually comes up with a really powerful model. Another thing that we unfortunately have to go through is the idea of convolution. So all these really cool image recognition algorithms use something called convolutional neural networks. So here I'm showing you a fully connected network. So no matter how we sort of permute these inputs, it's going to have the same meaning, right? It doesn't matter if the file size comes first or the file size comes second. We can sort of shuffle these things around. However, with image data, if you were to shuffle the pixels around, you lose the meaning of what's the image entirely, right? So what we do to deal with this is instead of using matrix-matrix multiplications in each layer, we use convolutions. A convolution basically is going to be taking an input image, and then you have something called a convolutional kernel that sort of steps over it. So every single row and every single column will have this convolution filter applied to it. And so what it's doing, mathematically, is it's taking, and since my laser pointer isn't here, I'll mouse over it. We're going to have an input image here, and we're going to have our convolution kernel here. And every single overlapping pixel, so this 0 to this 4, we're going to multiply together. So we do 0 times 4, and 0 times 0, and 0 times 0, 0 times 0 again, 1 times 0 again, 1 times 1, so on and so forth until we get to all the overlapping pixels. Then we're going to add all those up, and the filter response for that particular pixel is going to be -8. So we copy that over to our output image. We're going to do it again for this pixel, again for this pixel, again for this pixel, until we've stepped through the entire input image. So what are these convolutions doing exactly? Well, it's a really general operation. You can use them for edge detection. So in this case, we have a convolution kernel that's going to look at a top pixel, a bottom pixel, a left pixel, and a right pixel. That's going to be a weight of 4, right? 1 plus 1 plus 1 plus 1. Then you're going to subtract out the center pixel with the same weight, -4. And what you get is sort of like a rising, falling edge, an idea of where the edges lie in the image. So if you're trying to do a classifier that, let's say, distinguishes between men and women, you could maybe use the edge filter to come up with useful features. Like I said, it's a really general operation. You can also use it for blurring. So in this blurring example, we have all you're doing is you're just taking the average of the neighborhood of pixels, and this has the effect when you look at the image of blurring things out. So how do we use these in neural networks? So what we're going to do with a neural network is we're going to have, instead of weight matrices, we're going to have these convolution kernels. And the convolution kernels are going to be completely learned from the data. We're going to have convolutions followed by the element-wise nonlinearity I was talking about. When we do this a few times, then we have something called a pooling layer. The objective of the pooling layer is to look at a whole bunch of, let's say, 2 by 2 neighborhoods of pixels and do something like look at the maximum pixel for all of them. So in that case, you can turn a 64 by 64 image into a 32 by 32 image. And that has the effect of sort of reducing the dimensionality without hopefully throwing away too much interesting data. And you do this again and again until you get to the output layer. And then if the convolution filters have been learned well, and the fully connected layer has been learned well, then it can tell you the difference between cars and trucks and airplanes and ships and horses. So how do we interpret these models, right? So what I'm showing you here is the first hidden layer, in other words, the first set of filter responses. What you can see it's doing is it's sort of figuring out, the light parts of the image, the dark parts of the image. It may be coming up with edge detectors, things like that. Then as we run it through the rest of the model, what you tend to see is it starts picking up objects, right? So instead of just considering the light parts of the image and the dark parts of the image, it may be combining that information together into, sort of like, what does a wheel look like? Or what does a windshield look like? Or what does a trunk look like? It's combining all this stuff together to come up with a model that can tell the difference between a car and a horse. So what I'm showing here is the final output layer. So we're basically taking, I want to say these, and then just overlaying them on the car image. And what you see is it's picking up really highly right here. So this may be a filter that's really sensitive to detecting windows and cars. Maybe that's what its job is. Then you have other things that seem to be looking at the car as a whole. You have this one here that looks like it's looking at a headlight and grille. So it's combining all this information together to come up with something that can discriminate between a car and something else. So how do we use all this stuff for malware detection? I'm going to describe our model. So what we're going to do is we're going to disassemble a PE. We're going to turn it into a list of instructions, right? So we're going to have human readable mnemonics, and then we're going to turn it into just the hexadecimal encoding, right? And this hexadecimal encoding has a binary representation, and that's all we're doing here. So we take this 5.5, the thing that corresponds to the push RBP, and we're going to just put its binary information down here. So this is going to be the binary representation of 5.5. We're padding this out to 8 bytes because x86 instructions are variable length. This one's 5.3, so you can see it's only differing by 1 bit. This is the 4889FD. We're just going to do this to every single instruction until we have an image that is 64 pixels wide. In other words, 64 bits, the number of bits in the instruction. And it's going to be however many instructions we have in the executable D, right? So that's how tall the image is going to be. Then all we're going to do is we're going to take these image recognition algorithms that work really well with object recognition and apply them directly to malware detection. So we're going to have a big data set of Windows PEs. We have, in advance, we know which ones are good and which ones are bad. We're going to turn them into these sorts of images. Then we're going to throw it through a model, see what it says about it, and then we'll be done. So you can see sort of the spatial structure in the instructions. You can see sort of repeating sets. They kind of remind me of there's a Stephen Wolfram cellular automata, if you've ever seen those. They're sort of, they get a little noisy sometimes, but there's still definitely these patterns in the chaos, right? So the one unfortunate thing about this model and the thing that we had to figure out was the fact that with the object recognition algorithms, they always take in a fixed image size. So if you have a 512 by 512 image and you want to classify it, and your neural net only works with 64 by 64 images, you have to take your input image of 512 by 512, squeeze it down to the size it needs to be, and then you feed that into the algorithm. As far as I know, there's no way there's no compression thing you can do directly to PEs that makes sense, right? You could maybe truncate instructions, pad it out to some maximal length. That's going to waste a lot of memory. So what we do instead is we have this idea of sort of only feeding what the model thinks is important to the final fully connected layer. So in this case, the model sort of learns which instructions it needs to consider to call something good or bad. And what I've done here is I've sort of visualized it. So we have red being the sequences of instructions that the model thinks are important, and then white are the sequences that aren't important. Unfortunately, I haven't done a lot of data sciencing on these images. I think it could be really useful to reverse engineers. It could maybe give them, sort of a first point to look at in the executable or something like that. So for future work, static disassembly is really problematic, right? It's a very heuristic thing. There's no way that you can step through an executable and extract out every single instruction, right? There are going to be some things that you jump into conditionally, and it may not grab that. So how are we going to extract out all the executable code that we can? It's a difficult problem. Another difficult thing is that information can be buried elsewhere in the executable. You can have packed examples, you can have obfuscated examples. So we need to come up with ways to deal with this, right? Because the model that's just working on the disassembly data is going to have no visibility into the packed part of the executable. That said, there may be regularities in malware. So the malware may be doing something that makes a reverse engineer have to try really hard to unpack a sample. And that information may give you all you need to call something good or bad. Also, this code, or this model, only really applies to executable code. So it would be really cool to come up with ways to apply this to scripts. I think it would also be interesting to start applying this model to code running in VMs. So we could almost immediately start applying this model to Java. We could start applying it to C#'s intermediate representation. And as long as you add enough input samples, this approach could probably work pretty well. Another interesting thing I'd like to look into is the question of whether or not training on raw bytes is this tractable, right? Because if we have disassembly data, you may take like a 20 megabyte PE and has a whole bunch of images or something like that on it. And when you disassemble it, you may wind up with, several hundred kilobytes of disassembly information. So for the disassembly model, it's going to be very small and very compact and easy to train. But if you're training on raw bytes, it gets much more difficult, right? Because you have to consider every single byte, and that can be very, very large for some PEs. So with that, I'm going to get to the demo. So before I started this talk, I downloaded 100 samples from VirusTotal, and I'll show you the query that I'm using. In this particular one, we were grabbing any samples that are less than 3 megs. So if it's larger than 3 megs, we just throw it away. They were first seen 3 days ago or later. They're of type PE-EXE because that's what our model is trained on. Has more than 20 positives, so the industry as a whole thinks this thing's pretty nasty. And then we just have a tag in here that if the PE is corrupt, we toss it out because we don't want to disassemble it. Then we're going to grab some scans so we can see how this model compares to industry. And we're going to do some stuff that throws out samples that are .NET, for example. So if we disassemble a .NET sample, we only wind up with one instruction, so there's not much useful stuff the model can do with it. Then we're going to convert it into a thing that Julia, the programming language I implemented this, can understand. And then we're going to score it. So I'm going to run this model on the data that I downloaded before I started this talk, and we'll see how it does. I have no idea. So I'll full screen this.
We'll explain the graph too.
All right. So what we're seeing here is we're seeing a count of how many times okay. We're looking at the model's output probability, right? So you feed in a sample, then you get some output probability as to whether or not it's malware. If it's 0, then it's probably good. If it's 1, it's probably bad. So we're counting things up. We're seeing that we have a lot of detections at 1.
So the 1 will be on the right and 0 on the left.
Oh, yikes.
The numbers
Okay.
are cut off on the
Sorry
on the
about that.
protector.
So the interesting thing to point out about this is that there have been very few development hours that went into this project, right? And it's comparing somewhat favorably with the rest of industry, right? It's picking things out not at a super impressive hit rate, but the fact that this model can run on a whole lot of samples and sort of filter things down for reverse engineers to then look at is pretty interesting. So let's now run a scan program to see how well industry did. So I got to grab these scans first. This will take a moment. So what I'm going to do now is I'm going to see how well industry did with all of these samples, right? So I'm going to look at all the query results from VirusTotal and then anonymize the vendors, and then we'll see where we fall. While this is running, go ahead and open up Julia. All right. So we can see with the scans so far, not all of them have completed, but as I talk, more scans will go and we'll see how it winds up. We're falling roughly into the, I would say, a little bit lower than half. We're somewhere here. Whoever vendor 54 is, we're doing slightly better than. And as these scans come in, I'll go ahead and give you the 3 takeaways from this talk. Basically, throw disassembly data into a neural net, then the neural net does stuff, profit. I suppose while the scans are going, I'll start taking questions. If you don't happen to ask the question, if you don't have a chance to ask your question, you can contact us at machinelearning@silence.com and send us any questions there. I'd like to give a shout out to Derek Suter and Gabriel Acevedo. Without them, there would be no data for this project, and it just wouldn't have happened. And as an extra plug, we are hiring, so check out silence.com/company/careers and see if you'd be interested in anything. That'll open the floor to some questions. Yes? We turn on the mics?
Can you, oh,
Yeah.
okay, here we go. So Karpathy's blog post about text generation with recurrent neural networks use 2 or 3 layer networks.
Right.
And I was under the impression that deep learning referred to using much more layers. I was wondering what that was about. Like, is that deep learning? Or?
So I would say technically deep learning is any neural net that has, I guess it depends on who you ask. It has more than maybe, let's say, 1 hidden layer, you could call it deep. Some of the more sophisticated models like the googly net use up to like, I think 22 layers. Each layer is doing some sort of like crazy thing. So yeah, they can there's a pretty wide range for the definition of deep learning. I would call 2 layers deep. In this particular case, we have 2 convolutional layers followed by 2 fully connected layers. It's not super deep, but I would still call it deep. Yes.
So my question is, with the blog post you had on earlier and yours as well, you're using, so the blog post uses letters as the primitives and you're using just the opcodes. Is there a reason why you're not using like the AST for your code or words for the generation for text?
So you're asking why we're not using things like ASTs?
Yeah, why you're not using ASTs, and the blog post you had up earlier uses letters rather than words as the things to operate on.
Okay. You could certainly figure out a way to sort of leverage ASTs. I think there are some models that sort of work, like neural network-based models that work on tree structures. So that would be an interesting line of work. But yeah, that's, with research, there are a million different ways you can go, and that's just one particular direction I didn't go.
Okay, thank you.
Sure. Next question. Yes? Okay, so the question was, what is the biggest data set we validated this on? As far as training, let me think about this. I think I had about 1.6 million samples going in. And then I divided it about 90% for training and 10% for validation. So somewhere in the neighborhood of several 100,000 samples, maybe 100 or 200,000. Next question.
Hi, I was just wondering, do you know what percentage of the samples you're trying to classify are actually benign versus malicious?
So with the validation set that I have, it's a 50-50 split. Well, I think it was slightly less than 50-50, something like 60-40. But when I train the model, I give it a perfect split between good and bad, so it doesn't learn to unfairly bias one label over the other.
Okay. I mean, the reason I ask is like, obviously those proportions are like a lot different than you would find in an enterprise network or something.
Oh yeah, absolutely.
So, you could just make a sensor that always says this is malicious, and it would get it right 50% of the time, which would look better than some antivirus. But that's not really realistic.
Yeah, that's very true. The whole idea of like how our input distribution in training differs from the input distribution in like a likely situation, like when you actually run a machine learning based AV. It's one of those questions that's really hard to grapple with, right? Because knowing the input distribution is a really hard thing. Yeah.
I guess I'm just wondering, have you tried running like, with maybe 10,000 benignware and 1 malicious and seeing if it finds that one needle in the haystack or not?
I have not tried that, no. I can say as far as our production model goes, it's not super false positive-y. But yeah,
Yeah. Okay, thank you.
sure. Other question?
So with a training set of 1.6 million samples, it's obvious that they haven't been manually analyzed and labeled. So like your labels may not have that much confidence. How do you protect against just repeating the mistakes of existing AV?
Yeah, good question. We have observed that there's like a particular amount of label noise, right? So we may find that, you know, somewhere in the neighborhood of 1% or around there of labels are kind of like not very good. So there is that problem. Fortunately, a lot of models are fairly resilient to that. In other words, you don't have to worry too much about label noise until you start getting into the regime of like 5, 10, 20%. So as long as the labels that you get are kind of okay, your model is going to work pretty well.
So how do you tell which labels are good?
Unfortunately, that's one of the sort of getting into the range of trade secrets. There's a lot of work that goes into it, and I can't talk about that too much. Any more questions? All right, cool. Thank you so much for your time. I really appreciate it.